Hello.
Hello?
Do you see the slide correctly?
Yeah, we can see the slide and heard your voice.
Okay. But if I go into presentation mode, like I will check again.
Thank you.
And now, do you see it?
Yeah.
Okay. But I'm afraid I can't see your status.
Yeah.
I see. Um, so when do we start?
Okay. You can start by now.
Oh, okay.
Okay.
So, sorry, but is it 1 hour talk, right? Or
Yeah.
yeah,
It's the 1 hour talk. Yeah.
and then including some
Question.
Q&A.
Yeah.
Okay. And is it is Q&A on fly or at the end of the talk?
It's up to you.
Okay.
Yeah.
So then um, please ask any questions on the fly and also at the end if you want.
Okay. Thank you.
Mhm. Okay.
Okay.
Then let me start. Um, Thank you for having me here today. Today, I'm going to introduce my work, our work, uh, with joint work by my supervisor, Robert Koenig, um, about long-range data transmission in a fault-tolerant quantum bus architecture. Um, Basically, the title is about quantum bus architecture, but the paper is mainly about long-range entanglement generation. So I'll briefly introduce what does that mean. So let's consider um, a situation that there are R parties aligned in one dimension, and each party consists of m qubits initialized in 0. And what we want to do is creating a very long.
I'm sorry, do you change your slides? Because now your slide is in the first in
Oh,
the cover slide.
I see. I think something is wrong. Sorry. um,
Oh,
and
yes, it changed. Yeah.
yes, but but then I have to scroll manually. I'm afraid. This is not very optimal though. Okay, then yeah, let me start again. So we are considering the situation where our parties are aligned in one line, and I will call every party called um, repeater. And what we are going to do is constructing one very long bell pair from A1 to AR. And I will call R the communication distance because one natural application for this is using this bell pair for example, teleportation. So there are some restrictions um, for creating a state between A1 and AR. So basically, we really want all 2 qubit gates are applied on the qubits at the same repeater station or nearest neighboring stations like AJ and AJ plus 1. And we want a protocol such that this long bell pair, this long distance state is close to bell state in terms of fidelity. So we expect the fidelity is greater than 1 minus some constant times p, where p is somewhat parameter, which stands for the strength of the noise. And I will explain what kind of noise we are going to deal with later. And we want this protocol to be scalable, which means as we increase the number of qubits m, this number m, we expect r to be greater. But we also want this protocol remains a constant depth circuit, which means even if we increase m and r, the circuit depth should remain constant. And I will call this property low latency. Okay, here's the diagram for this low latency. Starting with 0 state, we apply some unitaries U1 to U delta, and we measure out all the qubits except for 2 qubits. One would be in A1 and one would be in AR. And then according to the measurement outcome, we apply some local operations. And the final state would be the state after this correction term x and z. But first, let's forget about this correction term and focus on the unitary. Here, each uj consists of 1 or 2 qubit gates. And these 2 qubit gates are restricted, as I said before. They must be on neighboring stations. So I will then begin with very well-known examples, which is entanglement swapping. If we have 3 parties, and if each party, each neighboring parties share Bell state, and then we can perform so-called Bell measurement, and then according to the measurement outcome, if we apply some appropriate local Pauli operation on A or C, then we can get a Bell pair from A to C. And we can consider somewhat successive way of doing this entanglement swapping from A to R. But the problem is if there are some noise which is applied to every qubit independently, for example, but then this outcome, rho A1, AR, would be not very useful because the probability of having the correct Bell state would decay with R exponentially. So this is not really what we want. And there are some strategies to overcome this with purification. which was suggested in 1999 by Duo and other authors. But this improved way is, of course, not low latency, what I explained before, because this purification step needs many states, and then they somehow combine their not perfect states to get a better Bell state. Another example I would like to mention is quantum percolation by work by Asin, Sirac, and Levenstein. So here they considered a 2D lattice structure, and then in the lattice, every edge represents somewhat shared state, phi, and these phi's are not maximally entangled state. And then the trick is they transform this shared phi into maximally entangled state. And then by percolation theory, there are some path between two nodes with some probability, of course. And then they use these paths to connect two nodes. And there are some nice theory about combining this percolation with entanglement swapping in some lattices, transforming hexagonal lattice to another lattice, triangular lattice. And there is some advantage compared to using only classical percolation theory. But I will not really go into detail because this is a little bit different approach from ours, because here every operation is assumed to be perfect, but the sort of error source is just the shared, not perfect, not maximally entangled state. Okay. In this slide, I just summarized only a few prior works on quantum repeaters and this entanglement generation problem. So here in the work by Muralid Haran and Lee and other people, they classified many schemes into three classes. So in the first generation, people thought about heralded entanglement generation and entanglement purification, as I told you before. But they assume some heralded protocol. So they somewhat know whether entanglement swapping was perfect or not. In the second generation, they somewhat used quantum error correcting codes to deal with operations error. And the third generation, people used error correcting code to address not only operational error, but also qubit errors. So our protocol, to be explained later, is sort of in the third generation, but in many schemes here are not really low latency, because their schemes are they successively somewhat transmit their information from A1 to A2 and A2 and A3 and so on. And every step they perform error correcting. But in our case, we don't really have any intermediate error correcting steps, so it's a little bit different. Okay. So from here, I will explain more about our protocol. So if there is any question.
No questions.
Okay, then I'll just go through. Okay, so in our paper, we give somewhat very concrete proof of threshold theorem, what we called. So this is the statement as follows. So we show that there is some number P0 between 0 and 1, and a family of pairs M and R, such that for any local stochastic noise of strength P less than or equal to P0, the fidelity is greater than 1 minus C times P. So here, I will repeat, F is the measure how the final state rho A1 and A are close to the Bell state. So the natural question is, let's say we fix R. And then what is the minimum number M, the number of qubits per each station, for this fault-tolerant entanglement generation of distance R? Or equivalently, one can fix R, one can fix M, and then what is the maximum communication distance? And in our protocol, we have, if we fix R, then we only need log square of R, number of qubits per station. So here is kind of a summary of our protocol. Our protocol is low latency protocol, and it consists single or 2 qubit Clifford unitary gates. And as I said, we only need M log square of R number of qubits asymptotically. And every gates acting on qubits are geometrically local. This is the property I said, that every 2 qubit gates are on the qubits on the same repeater station or nearest neighboring stations. Before the real explanation about our protocol, I have to mention the noise model that we are considering, which is called local stochastic noise. So the definition is we consider a Pauli error E, which has the following property. So we say E is a local stochastic error with strength P if the probability of E, oh sorry, here is the typo, E I'm sorry, here, yeah, here it should be like Yes. So let's consider this Pauli operator E. Here it's X tensor I tensor Z tensor I, and then the support of E is the qubit 1 and 3. And we want the property that the subset F of subset of 1, 2 to N is contained in this support. The probability of that event is less than or equal to P to the cardinality of F. Okay. So for example, the IID error on each qubit with probability P over 3 for each X, Y, and Z error is a local stochastic error of strength N of P. Okay. So let's go back to our circuit diagram. So here we have N, which is the total number of qubits. N is equal to M times R. And we are considering circuit level noise, which is affected by E0 to E delta plus 1. And here at the end of the circuit, I put E delta and E delta plus 1 there to indicate E delta is used to indicate the error affected by the gate U delta, and the last one indicates the measurement flip error. So here I have U noisy, which is just this whole unitary including error. And here I need to mention that EJs are not necessarily independent. They might be somewhat correlated.
Sorry,
Yes.
can you remind me where does the two measurement qubit they are acting on? The two measurement?
Do you mean this one?
Yes. They are measuring on the first and last one, the A1 and AR.
Oh yeah, okay. So in this diagram, you may think the first one A1, one of the qubit in A1, and the second one of the qubit in AR, and all the other qubits are measured, but I only drew 2 qubits here.
Oh, okay. So only two are not measured. A1 and AR not measured. All the rest are
Exactly.
measured.
We measure all the qubits except for 2 qubits, one in A1 and one in AR.
Okay, okay, thank you.
But here, if we only consider Clifford unitaries, then there is a rule like EJ times UJ plus 1 can be written as UJ plus 1 times EJ prime for some Pauli EJ prime. Using this trick, we will commute all the errors from E0 to E delta minus 1 to the next to the unitary U delta. And making the product of all these commutative Paulis we get one Pauli error E at the end of the circuit just before the measurement. But we have to consider like this commutative Pauli error can be a little bit stronger than the original one. And here are some known facts by Ravi and other people that this commutative Pauli errors are still local stochastic noise, but they have different strength. They actually they actually have stronger strength. And if we multiply two local stochastic noises, then the strength can be written in this form: 2 times maximum of square root of p and square root of p prime, where p and p primes are the strength of the original local stochastic noises. So using all these tricks, we can say that our noisy circuit is nothing but the original circuit U1 to U delta, and affected by some error, local stochastic error, with strength P to the C, where C depends on delta. But as I said, our protocol will be constant depth, so delta would remain as constant. So we will just say, okay, U noisy is just affected by local stochastic noise of strength P. And many people call this error the phenomenal error. And we sort of reduce the problem of general circuit level noise into phenomenal error problem. Okay. To explain our protocol, we need to know two ingredients. One is fault-tolerant decoding of 2D surface codes, and the other thing is fault-tolerant preparation of logical Bell state using 3D cluster state. So I'll briefly mention what is 2D surface code for someone who are not really familiar. So it is a quantum error correcting code where qubits lying on 2D surface, and each qubits are represented as sphere on the figure right hand side, and I will denote the number of qubits by n, and here n is equal to 2d squared plus d minus 1 squared, where d is called the distance of the code. And the stabilizer generators are denoted by AV and BF. AV is called a star operator, and BF is called placket operator. And we consider the stabilizer group generated by all AV and BF, where V are vertices and Fs are faces of the lattice. And the state stabilized by all the elements in S consists of the code space, and the dimension of this space is 2, which means we can encode one logical qubit. And we also have logical operators X and X bar and Z bar. And they are defined as the product of X on this vertical strip or the product of Z's lying on this horizontal strip. They have this commutation relation. So X bar and Z bar, they are anti-commute. And X bar and Z bar commute with all the stabilizer operators. And we define logical 0 and logical 1 by the following equation. They are basically eigenvectors of Z bar. And logical 0 corresponds to eigenvalue 1, and logical 1 corresponds to eigenvalue -1. So what we need is so-called single-shot decoding of 2D surface code. Let's consider we have an input state psi bar, which is alpha 0 bar plus beta 1 bar, which is an encoded state of 1 qubit state psi alpha 0 plus beta 1. And what we want to get is the original state psi given the input logical state psi bar. And then here's the process. So we somehow partition the set of qubits into 3 subsets, Q and X and Z. And the process is we measure out all qubits except for 1 qubit called Q. And we measure all qubits in X in Hadamard basis or X basis, and all qubits in Z measured in computational basis. And I will denote the measurement outcome by S, which is nothing but a string, binary string, supported by X and Z. And according to the measurement outcome, we apply some local correction operator, Z to the A S and X to the B of S on Q, where A and B are classically computed. And there must be some output state on Q, which is single qubit state, and we want to expect that this output state would be the original state psi. And we want this process to be fault tolerant, which means in spite of E, the error, we want this happens with some constant probability. So this helps you to understand what's going on given an input state psi bar. We measure some qubits in X and some qubits in Z. And according to the measurement outcome, we classically compute A of S and B of S. And according to A and B, we apply local Pauli operation and we get psi out. Okay. But one can show that psi, the post-measurement state, psi PM, is one of the states defined as here. So psi is always psi PM is always one of the states, psi or z psi or x psi or zx psi. So this decoding problem is essentially given the measurement outcome S, we guess what were C and D. So in our paper, we proved the following theorem. If the local stochastic error had strength less than 1/144, then this output state is proportional to the original state with probability greater than or equal to 1 minus 94p. And here is the diagram. What was the set X and set Z, which has this triangular measurement pattern. Here, I would like to mention that this pattern was first studied in this paper by Persekurs in 2010, and also by Mazurek and other people in 2014. And Litinsky, relatively recent paper, here Litinsky used this measurement pattern for logical T-gate measurement, and our result subsumes is logical measurement because after our protocol we get single qubit state, and then we can perform T measurement. Okay. So as I said, A and B are computed by some classical machine, and they are nothing but minimum weight perfect matching, which is pretty popular in quantum error correcting. So given the measurement outcome S, we somewhat know the boundary of the error, which is called syndromes. So in this figure, according to S, we can compute that there are some positions marked in this diamond, which represent the boundary of the actual errors. And what we do is finding minimum weight perfect matching. And those matchings are represented in blue rectangles. In this case, we somewhat corrected the error correctly because there is no logical error. But if our matching, or in this case, then there is a strip connecting from left side to right side like this. And in this case, there is a logical error. So in this case, the protocol fails to retrieve the correct state psi. Okay, that was one one of the main ideas for our protocol, and then I will move on to 3D cluster state.
Hi. Hello.
Yes.
So I was wondering, so you, in your method, you first doing some swap and later doing those unitaries, like you want to use triangle, and later you're doing this error correction to correct the error. Is that true? Like am I correct? Like the procedure?
Oh. So we don't really use entanglement swapping, but I just introduced them because they were very famous example in entanglement generation schemes.
Then, like so, so you start with a product state, then you just use those U1 to U triangle.
Yes, yes.
And using error correction, then you can at the end you will get the fail state.
Exactly.
Okay, but then for those unitaries, are they just? I mean, you draw like it apply on every qubit, like is I mean, I imagine isn't it just apply on like nearby qubit and next nearby qubit and to the are they for adding on all the qubits?
I see. So maybe I will move a little bit further and then briefly explain what's going on.
Yes, thank you.
Yeah. So we are actually considering this 3D cubic state, and consider there are sheets, R number of sheets consisting this cube, and each so considering this cluster state, we only need nearest neighboring gates. So they are what I call U1 to U delta, and the depth is only 6 because the degree of this lattice is 4 and we need some single qubit operations. So the depth is only 6. And then we perform some measurements. We measure out qubits in the middle first, and then we measure out all the qubits except for those green qubits, like this. And then we only have 2 qubit states. And then according to the measurement outcome, we perform local operation, z to the A and x to the B. And then the final state would be the best state with some probability. That's the protocol.
But at this stage, so you have you are doing this many times, so you can correct it or I mean you just you just go through once and you can decide which operator you are applying on them to correct them.
Yes. So this is
okay.
a single shot.
Okay.
Yeah. So we only measure all the qubits. So every measurement is just single qubit measurement, and then from the single qubit measurement outcome, we apply some local correction.
Okay, thank you.
So we don't have to repeat. Of course, you can repeat and then use the outcome for purification, but that's not really what we want.
Okay, thank you.
Okay.
Sorry, I kind of have confused. You encode the toric call or to surface call on each 2D sheet, right?
Ah,
And do you need error correction for each sheet, or you don't have to? You say only do a single shot at the end. So
yes, yes. Okay,
what's the case?
yes. So I introduced this 2D surface code because one can think of this as follows. So if you have this cluster state, it is pretty well known by Rausendorf, Ravi, and Harrington that using this cluster state, you can generate a logical bell pair lying on the opposite sides of the cube,
Uh,
right?
so
And
you say,
then,
mm-hmm.
sorry,
You say it again. Sorry, you say you apply what can have the two-side qubit.
okay. So the process is you measure out all the qubits except for the qubits on the sides.
Okay.
And then there is some local operation which is computed by some matching like error correcting codes. And then if you apply those local correction term, then you get the logical bell pair, which is encoded in 2D surface code.
Mm-hmm.
So basically you get logical 0 plus logical 1 state with some probability.
Okay, I see.
And then you can consider applying our single shot decoding scheme on each sides. Then you will get two qubit bell pair.
Each side means the whole layer two side, the first
Yes,
layer and
yes.
next
So
layer. Okay, I
in
see.
this diagram, so this is the famous scheme by Brabi and other people. So measure all the black qubits, and then there are two sheets lying on the opposite side in the cube. And this state, with some correction operator, they form the logical bell state. Logical 0 plus logical 1. And then consider applying our single shot 2D surface code decoding scheme. Then you get this green 2-qubit bell state. That's somewhat intuitive idea of our protocol.
I see. Thank you.
Yeah. I'll move to the next part. So this naive version of our protocol is theoretically okay, but the threshold bound obtained by this naive composition is not very good, which is almost 0. So we consider the combined version of two protocols. So as I told you, constructing this logical bell pair, we need some correction operator, and this is computed by some matching like quantum error correction. And we apply again correction operator using matching. So what we did is essentially combining two steps into just one step of quantum error correcting like matching. That's what we did. And this idea is essentially studied by Persigors in 2010. But in his work, he considered somewhat restricted error model. He only considered phenomenal z error on the logical bell, on the cluster state or logical bell state, but all the measurements or local operations are considered perfect. So in our case, we considered circuit level noise, but using local stochastic errors, we somewhat avoided this problem, and we proved for the phenomenal case of the local stochastic error. Okay. And we also considered long entanglement generation using very long lattice like this. So not using cube, we use this elongated version of the lattice. And you may consider each slice consists of one repeater station. Okay. So this is our threshold theorem. If we are given some parameter p less than this number, 1/5000, and if the communication distance is less than this number, which is exponential in the code distance d, then we have this nice property that the final state is steady state in with probability greater than or equal to 1 minus some constant number times p. We also consider the converse problem, which is what is the maximal distance for this entanglement generation if we use low latency protocol, or is this R that we obtained is asymptotically tight or not? And we have affirmative answer yes to the latter. To this problem, is the asymptotic bound on R tight with our protocol? You can see the argument in our paper. But there is a certain gap between our protocol and what we theoretically obtained from the general low latency protocol. So we only proved that if we use low latency protocol, we need at least log R amount of qubits per repeater station. But using our protocol, we only proved n is equal to log square of R. So there is a certain gap, log R amount of gap between this bound and what we obtained from our protocol. Okay. Let me briefly introduce the ideas in the proof of this m equal to log R bound. Roughly, what you can just consider depolarizing channel, and then this depolarizing channel breaks the entanglement between two parties. And if R is too long, the final state must be separable state across AJ and AJ plus 1 for some J. So imagine like if R is too long, there is some weak link, very weak link, so that it is broken by depolarizing channel. Maybe this is a very rough idea, but you can check our paper, and it is not very difficult.
Sorry, you
Yes.
mean separable means exactly separable or just nearly separable? You
Exactly
okay.
separable.
Okay.
Maybe you can consider somewhat relaxed version, but to prove our bound, it was enough to only consider exactly separable case.
Okay.
So if it is separable, there is no there's no entanglement at all. So the fidelity between the Bell state is not greater than 1/2.
Uh-huh.
Yeah. Finally, we arrived to the quantum bus architecture, what appears in our paper's title. So we use this protocol to the application for non-local constant weight measurement. So if we have a very big number of qubits, what we want to do is, for example, stabilizer measurement on some subset of qubits where the cardinality is just constant. This might be a problem because they are not locally positioned. And what we do is just transmitting those qubits, green, red, and blue qubits, to the right-hand side of this architecture. This is possible by our protocol, the long-range entanglement generation, and then use the entanglement to teleport those qubits on to the right-hand side. And then they are positioned locally, so we can easily perform measurement. And after this constant weight measurement, we teleport them back so that so those qubits are teleported back to the original position. Okay. So here's the summary of our work. So we gave a rigorous proof of the threshold theorem of the long-range entanglement generation using elongated 3D lattice. And then we also gave a proof that our suggested distance, communication distance, is asymptotically tight. But we also gave a proof that if we consider the general low latency protocol and this very easy idea of using depolarizing channel with entanglement breaking, there is a certain gap between this general model and our model, and it is still open. Okay. So this is the end of my talk. If there is any questions, please let me know. And here are the references.
Is there any questions from the audience?
Sorry, can you explain again what's the gap you mean?
Okay. Yes. So using this idea for using this separability idea, then one can show that if we are stick to low latency protocol, then to achieve this constant fidelity, you need at least log R amount of qubits per repeater station.
Yes.
But in our case, we only proved that if m is equal to log square of R asymptotically, then we get constant fidelity.
Okay, I see.
Yeah. So it is unknown whether there is a low latency protocol which achieved this bound.
Oh, okay.
Yeah. So our protocol is low latency protocol, but this our protocol does not achieve this bound.
I see. I see.
Yeah.
Sorry, the naive question. What exactly the low latency mean? It means with
It
fixed
means
MN.
yeah, it means it can be represented as adaptive constant depth circuit with some correction operator computed by classical computer. So yeah, so it consists of U, unitary U, and then which is followed by measurement, except for 2 qubits in A1 and AR. And the depth of the circuit should be constant with the restriction of uh, geometrical locality.
Okay. Then why it is adaptive?
Um, in our case, we use adaptivity for only for the final local correction operator, but you can generalize that any uj can be adaptive by intermediate measurement outcomes. But in our case, it is not really adaptive, but you can prove the adaptive low latency protocol needs at least log R amount of qubits.
Okay. Okay. Thank you.
So your protocol so your protocol cannot reach the low bound the n equal to omega log r, right?
Exactly, exactly.
So is there any protocol have the m value in between your value and the lower bound?
That's a very tricky question because many quantum repeater papers do not really account to circuit level noise, but only for IID noise in phenomenal error. And so there are not so many comparative researches actually, and I'm afraid not so.
I see.
Yeah.
So is it possible to prove the lower bound is not too small?
Sorry, say again.
Is there any chance to prove the lower bound is not too small? Maybe yeah.
I see, but we expect this bound is somewhat tight. which is what I mean is we somewhat expect that there is some protocol which achieve this lower bound, but we don't really know yet. And this cluster-based protocol, as our case, which is very, very promising, but with any correction operator, we cannot really achieve this bound. We also proved that somewhat side result.
I see. Thank you. Okay. Is there any further question from the audience?
Hello.
Yes.
I'm wondering, like, so the from A1 to AR, then how long is their distance? Like, this it looks to me it's like it have to be limited distance, or I mean, like in angle swapping, I think I can send some photo to the next site, but I think this is more close for you can do some similar thing.
So if I understand correctly, like, are you considering kind of physical distance between two
Yes.
neighboring repeaters, right?
Yes.
We didn't really consider kind of real physical distance between repeaters. So in many papers, if I understand correctly, like they somewhat use flying qubits, like photons, to for sharing Bell state in the beginning, to apply some two qubit gate between nearest repeater. And I think you are considering it that way, right?
Yes.
Yeah. We somehow have abstract version. So anyway, if you have a Bell pair, then you can use something like gate teleportation to apply 2 qubit gates on 2 qubits on two nearest repeaters. But we just say like, okay, you can apply 2 qubit gates with some circuit level noise. And our model is more general than this flying qubit model, actually. Does this answer your question, or?
Yes. I need to think about it.
Okay. Is there any further questions? Okay. If there is no further questions, let's thank Shin Ho. Thank you for the talk. Thank you.
Thank you.
Thank you.
Thank you.